In this tutorial, I'm going to present about one of the latest additions to the PuMA software, which is the capability of computing the permeability of workspaces. So I assume that you've already installed PuMA and are able to run just a Python project like here in PyCharm, and I've basically just prepared a small code example that I'm going to go through now. So the first step is that I'm gonna run is the generation of a domain that is made of artificial fibers. And I'm actually creating two different workspaces. The first one having completely randomly oriented fibers, and the second one having a preferential direction, basically oriented along the XY plane. So I'll run this, and actually something else that I want to mention is that I set up so that the runs are repeatable, and you can do that by setting the random seed in PuMA. So the first thing that it's going to output is a plot of the two workspaces. It's basically just 100 cube domains, and as you can see on the left, the fibers are completely random, and on the right instead they are oriented with the XY plane. So something else I wanted to also briefly mention is that PuMA basically relies on a 3D rendering dependency called PyVista, which I'm currently importing directly here together with NumPy. And this allows us to create more complex plots, such as the ones here, where I'm subplotting two different domains. So without further ado, I'm going to close this figure, and the compute permeability function is going to run on these two workspaces. The compute permeability takes a few inputs. The first one is just the workspace. The second one is a cutoff for identifying the solid phase. And in this case, it's from 1 to the maximum of the workspace, which is basically the highest ID for the fibers. And then in this case, I'm using a solver called minres and using a tolerance of e to the minus 7. So now the solver is going to run and compute the effective permeability for both the workspaces by running simulations in the 3 Cartesian directions. And what it's going to give us is basically a velocity and pressure field for the 3 directions, as well as the K effective, which is the effective permeability tensor. Okay, so convergence has now been reached, and so the two effective tensors have been output, as you can see up here and down here, the second one. So something else that I've added is also some plotting for the velocity and pressure fields that are shown in here. So we can go and analyze them a little bit. So in this case, something to note is that we're using periodic boundary conditions. So this is why on some of these surfaces you can see the reflection from the other side. And on the top instead, it's the velocity fields. So as you can see, for the domain that has preferential fibers, it is in the z direction, so the through thickness direction. We have a lower permeability, and so a lower mean velocity, also as you can see from the highest of these velocities. And if we can go and verify that in the permeability tensor, as you can see, the diagonal components for the first randomly oriented domain are more or less the same for the 3 diagonals. On the other hand, for the second domain, we have a higher permeability in the x and y diagonal, and instead for the z direction we have a lower one, and still it's lower than the first domain. So one more thing that I wanted to note is that at the end of this Python script, I've also added an export VTI function call, so that I can export basically every single permeability result that I've run so far, including the velocity fields, the pressure fields, as well as the 2 domains. So if I now go and as you can see, it has exported a VTI file inside my downloads, and I can now drag it and drop it inside ParaView. And there it goes, apply, and now I can basically show the same results as I did earlier for example, the velocity or the pressure, etc., the workspace, etc. This concludes this tutorial. I'll see you in the next one.